Okay, so thank you, Nikolai, for the introduction. And thank you for organizing this conference. Maybe he's not hearing, maybe he will hear this in the recording, even if he's not in this room. Yes, indeed, it was a pleasure that I was looking forward each time coming from the United Kingdom to St. Petersburg every April to participate in this conference, and of course to meet Vladimir Gert and see his smile and hear his experience his curiosity and his always very interesting questions. So this is a very sad occasion that we have to devote this conference to his memory. And well, despite the many talks I've given here, this maybe will be the closest to Polynomial Computer Algebra. And the basic problem is not about polynomials, and it's much easier to explain than the title, and it can be explained to 5-year-old children in the kindergarten. Because if you give two children a fair coin, and ask them to toss it 10 times, and give them each of them a pencil, so there is Alice and Bob, 2 kids, you give each one a coin and a pencil, they toss it 10 times, they get 10 bits, random bits, right? It's hard to invent random bits, as we know, artificially, but maybe it's something like this. And it's written in pencil, and then you give them rubber, and the task is to erase as few bits as possible so that the 2 strings are equal, right? So the longest common subsequence of 2 random strings. And, well, maybe I should use an eraser to erase. Well, maybe you can tell me what's the longest common subsequence here. I don't want to get it wrong. Well, I see 1, 0, 1, 1 here and here. This is not on purpose, but that's how it is. And then 0, 1 here and here. And also a 0, so maybe it's 7, right? So I'm just interested in the length. Well, it looks like I've invented sufficiently random strings because the expectation is 8. Okay? And now, of course, we are mathematicians, so we wouldn't be happy with just 10 bits. So let's take 100 bits. So Gennady and I toss a coin 100 times, and we do the same thing, right? And how many bits in common we should expect, what will be the length of the longest common subsequence? Nobody knows. I think this is amazing. This is an extremely surprising fact that it's anywhere. So let's call the proportion gamma, and for all we know, gamma is between. This is very recent, what I'm going to talk about, and very preliminary. So I'll be looking at various notes at various times. So I don't want to get it wrong. Without looking, it's I wanted more digits, but it's between 078 and 083. Okay, so we don't 79. I think 79. So we don't even know if we will get in expectation 79 or 83 bits out of 100. I think it's incredible that, well, we teach this problem in an algorithm, well, the longest common subsequence problem in an algorithms course in the first year, and everybody knows how to program it, and it's even if it's not a university course, you know, any programming course will probably teach that, and we teach probability and Bernoulli processes in first year probability, but put them together and we don't know an answer to this basic question. And of course, so the question is the value of gamma as n tends to infinity, and of course we can take an alphabet larger than 2, but let's just concentrate on 2, so let's call it gamma 2. And these bounds are obtained, well, they have been obtained in the 80s, I think, and slight improvements since, and there was a long time without an improvement. So they are obtained by combinatorics on specific strings. So the lower bound, you just have to sort of find specific substrings and strings long enough and common. And for the upper bound, you have to look at automata and automata accepting sufficiently long common subsequences, sufficiently long common subsequences, but the gap is still very wide. And of course, there have been experiments, and well, you can generate a very long string of bits, even if you have to run a quadratic time algorithm to find the longest common subsequence. So experimentally, we know that gamma 2, well, it's always going to be gamma 2, so let me call it gamma. That gamma is about 0.811. And this 3 is to 8. Okay, so how can we apply polynomial computer algebra to crack this, or at least to improve on this, right? So I'm concentrating on the upper bound. Can we do anything better than this? Anything better than looking at automata accepting strings? Maybe we can somehow use a continuous limit of this of a process that describes this. Well, maybe we can express this as a stochastic process and then take the limit and see what happens. So how do we do this? Well, this some of you may know. This is related to the longest common subsequence problem in general. Can I write on this board, or is it out of picture? Okay. So the longest common subsequence problem. Okay, and how it behaves when you concatenate strings. And the behavior is, so I have two strings, well, A and B, and A consists of A prime and A double prime, and B is just fixed. And I'm looking at LCS, longest common subsequence of A prime B, and LCS of the A double prime B. And I want to be able to tell something about LCS of A and B, right? And it turns out that this is a very interesting algebraic structure, which can be expressed in various forms. I call it the sticky braid monoid. And officially, it's called either the Hecke monoid or zero Hecke monoid, or some zero Hecke monoid of the symmetric group, and so on. because there are various generalizations to other groups. So what is all this about? Well, I don't probably have time to describe, well, let me just say that this is closely related to the classical Braid group and is described by a Braid-like structure. So let me just draw a picture. So let's say one string is A, B, C, A, B, C, A, and the other is A, C, B, C. And here I'm using an alphabet of size 3, as you can see. And what we need to do is to draw a graph like this and to mark the matches. So the match the A's and the C and the B and the C again. Okay, and now we make a braid out of paths in the dual graph. So, bear with me. It's, yeah, so I do it like this. And then on purpose, I use a different chalk. And I continue the braid here like this. Okay, so what is the main property that this sticky braid has? The main property is the idempotency of elementary crossings. So you can draw the braid any way you like. In general, you draw a crossing in an empty cell and a pair of non-crossing strands in a cell with a match, right? But then you reduce this braid by removing double crossings because the main property is idempotency and no two strands can cross more than once in a reduced braid. Okay, so this is how you think about, well, this is in some way the right way to think about the longest common subsequence problem. And now how else you can think about it other than braids? Well, you can represent this in a completely equivalent and also very familiar form. And if you read Knuth, the famous Art of Computer Programming monograph, and you take volume 3, which is sorting and searching, a large part of it is about sorting networks. So, and you stare at this and you realize that this is nothing but a sorting network, right? And in particular, a special kind of sorting network, which is called Transposition Network, or in Knuth's terminology, it's called primitive sorting network. What do I mean by that? Well, I mean that we can draw the same picture, but now instead of strands, let's have wires, right? So I have, I still have the matches. Okay, and now I have, now the meaning of the colors is going to be completely different, but now I have some wires stretched across the cells in this way. Okay, and and the wire carries some value, a number, okay? So, well, I forgot my color coding, so these wires should have been in pink. Okay, and now, whenever I don't have a match, I have a comparator between the two wires. So in general, the values move in this direction. There is a comparison between every pair of values that does not cross a match, like this. Okay, so this is a transposition network. Okay, so now I can give some input to this network, and I give an input which is sorted in reverse order, so in decreasing order. And let me just give it the bits 0 and 1. So the orange is going to be 1, and the pink is going to be 0. Okay. So now you can, well, if the values were all different, then the picture would be exactly like this, right? If the values are of only two kinds, like here, then you can interpret this picture in various ways. But what matters is how many zeros end up at the bottom and how many ones. So if you run this network, then you're going to have 1, 1, 1, and 1 here, and zeros everywhere else. Okay, so the longest common subsequence of this pair of strings is 3, because I just count the ones at the bottom, or I count zeros at the right. Okay. So this is useful. So now, how do I use this? There are lots of other ways to interpret this, as I say. So another way to look at this are well-known stochastic processes known as TASEP, totally asymmetric simple exclusion process. And then you have you have an array of sites which can either be empty, a hole, or contain a particle, and particles jump to the right with some probability q if there is no particle, if there is a hole to where the particle wants to jump. Okay. And you can put some initial condition on this, and you can study how this develops, how this process behaves. Okay, so if you look very closely, right, you can think of ones as particles and zeros as holes. So luckily, I only need to change ones to particles, and zeros look like holes already. I mixed up my color coding, so forgive me for that. At the bottom, never mind. In fact, there are two TASEPs here in this picture, because one goes this way and another goes this way, and they are coupled in some interesting way. Or you can, one goes this way, and the other goes this way. Yeah. So And now, one of the standard techniques that are applied to TASEPs is taking the hydrodynamic limit and write a PDE, a partial differential equation, and solve it and obtain the solution for the particles as a continuous mass as opposed to just discrete elements. Okay, and there are different versions of this, and all the versions basically have the form of so we need a partial differential equation to take this to the limit. So partial differential PDE, okay? And the right kind of PDE here is some conservation law that is about conserving this mass as the time flows. So so we need some conservation law, and in general it has the form of so let's call U the density of the particles. So it has the form of the time derivative of U plus the spatial derivative of the flux being equal to 0, where the flux is the rate with which the particles jump, and this is dependent on the actual structure as well, whether this is discrete or whether the time here is discrete or continuous, right? The positions are always discrete before we've taken the limits. The time can be discrete from the start on, okay, can be continuous. Depends on how if the time is discrete, it depends on how we update. Do we update all the sides simultaneously? Do we go from left to right or from right to left? So depending on all that, there is this flux function that describes the behavior of this process. So we assume that the flux is strictly concave. And we are interested in the step initial condition. So this is the step initial condition for the TASEP, right? So what do I mean by that? Well, we have 0, we have all the holes on the right, and we have all the particles on the left. So this is precisely the step initial condition for right? And the step initial condition for a TASEP is precisely what you have in a traffic jam, right? So you have drivers who drive very carelessly, and if a driver sees an empty space in front of him, he just goes at a steady rate, okay? If the driver sees another car in front of them, they are alarmed and slam on the brakes. And if so if there is a car, well, the driver stops. If there is no car, the driver sort of relaxed and thinks, and maybe he moves, or maybe he waits, right? And as in any traffic jam, you will see on a real highway, so there are two different ways in which the traffic jam behaves at the head and at the tail, all right? So if you drive and you see in front of you some traffic jam, right, and now you just stop, right? But if you now fly in a helicopter above this traffic jam, you will see that the tail of the traffic jam moves backwards at some constant speed, right? So we imagine, so the cars arriving from some density u to 1, and there is this shock wave that propagates backwards, and we are not interested in that, but we are very much interested in what is happening in front of the traffic jam. And what happens is that, well, the first car moves off at some constant speed, but then there will be very few cars following it, and in general there will be a sort of narrower angle at which the density goes from 1 to 0, from 1 to almost 0, right? And there will be this sort of space where it's almost 0, exponentially close to 0, and then it will be real 0. And the interesting things are happening in this rarefaction wave, or rarefaction fan. So how the density of particles goes from 1 to 0. Okay, so this is the solution to this partial differential equation. Okay, and I don't think I have time to write down the solution, but this is what we are trying to do. Well, this is, let me write down the solution for, let me go back to this, right? So how do we analyze this? Well, people have analyzed this, and the best they could come up with is the following. So it's very hard to analyze. It's sort of deceptively simple. This picture is extremely hard to analyze. The comparisons generated by a pair of strings. Remember that we start with a pair of strings. So comparisons generated by this pair of strings, and then the particles and holes running through this transposition network. So people have simplified this as follows. Let's pretend there aren't any strings. Let's pretend there aren't any 2 random strings of n bits each. Let's just pretend that we have n squared independent random bits, right? Mutually independent random bits. Okay? And if we have n squared mutually independent random bits, then this is precisely the T-sep, the discrete time T-sep with sequential update. And it's extremely simple to analyze because we have a comparison here. Let me just turn it 45 degrees. So if we have a comparison element, right, it can either be present or not, right? So if there is a mismatch between 2 characters, well, there aren't any characters now, but there's still, let's call it a match or a mismatch. If there is a mismatch, there is a comparison, right? And we have those 2 T-seps, well, these 2 T-seps going in opposite directions. So let's call, and they have different densities, which is sort of crucial. They have equal density if the density is 0 or 1, but anything in between them, they must have different densities because a comparison sorts and puts the smaller number on the left and larger number on the right. So the comparison that the T-sep that goes through the left-hand side of each comparison has to have lower density than the one that goes through the right-hand side of the comparison, right? So so let's call this U, and let's call this V, okay? And then we have, for a comparison, we have U and V coming in. So a particle coming in with probability U here and with probability V here, and luckily it can be proved that they're independent, and the comparison is independent, which is the simplification that I described. For my problem, they are far from being independent, but here they are. So if the comparison is there in sorts, then it's well, this bit is 1 precisely when both bits are 1, so this is just uv, and this bit is 0 precisely when both bits are 0, so this is just 1 minus 1 minus u, 1 minus v. And if there is no comparison, let's draw it this way, then if there is no comparison, then this is u and this is v, and this is still u and this is still v, and this happens with probability half, and this happens with probability half, and from this system of equations you get u and v, and you get this number eventually. This is 8 to 6, and 8 to 8 is the number that you get from that. This is called Bernoulli model. It's not a good name, I think, because the strings themselves are Bernoulli processes. But so for the Bernoulli model, gamma for the Bernoulli model is so this is just 2 square root of 2 minus 1. Okay, time is up. 2 minutes, 3 minutes? Okay.
Maybe 2.
Okay, maybe 2. Okay, and I still haven't approached the polynomial computer algebra. So let me describe in 3 minutes what's going on here. So now I have a much harder problem. Instead of mutual independence, this is of n squared bits. My original problem is just 2n bits, and the comparisons that they are 3-wise independent, but they're far from being, we have already, well, 4 comparisons can be prohibited if, well, if it's particle, whole, then we can only have, well, we can't have 3 of one kind and 1 of another kind, yeah? So this is only 2n independent bits instead of n squared. This is much more dependent. This is, we can no longer say that this comparator is one, there is no 1/2 here and no 1/2 here, and it's a lot of cases to consider which combinations of zeros and ones give rise to well, how they are interdependent with the comparator being present here, because remember there are strings, so this comparator may imply or prohibit some comparators above it, and those affect the v's and u's, so they sort of affect each other, and all this becomes messy, but we can use computer algebra. So let's just write this. Let's now think of v and u not as numbers, but as just bits themselves, particle or whole, right? So then this is obviously u and v, and this is obviously u or v, and this is obviously u and this is v, okay? And we can't attach probabilities yet, but we can now do this for larger grids, for the subgrids of this grid. So we can do this for a grid like this and a grid like this. And so on. And there will be some huge Boolean expressions here, some sort of polynomials in conjunction and disjunction here, okay? And what we can do now is we can program all this up in Mathematica, okay? And luckily, Mathematica has very nice tools for dealing with both Boolean algebra and polynomial algebra, okay? And what we need to do here is we have these huge Boolean terms, expressions that arise here, which are sort of messy trees of conjunctions and disjunctions, and turn them into perfect disjunctive form, I think it's called, or in Mathematica, it's called exclusive sum of products. Okay, exclusive sum of products. And because it's exclusive, then in that tree, Mathematica has wonderful substitutions. So you can substitute times for and because it's exclusive, you also substitute plus for or, and you substitute 1 minus, you can even substitute in Mathematica 1 minus x for not, and you get a system of polynomials. And you can solve it, well, in the case of one comparison, and this is still 3-wise, remember this thing is 3-wise independent, so this should give you this, and it does. And this is already getting into more interesting because these 4 are, they can't be 3 of one kind and 1 of another kind. So this is not 4-wise independent. So from this, you start getting some estimates that are better than this. And running this, and you know, I say this is very preliminary, so last night I was just running it, you know, I couldn't run it for hours, but I ran it for a few minutes, and it's 0 to 2, 8 to 2 here. So 8 to 2, 2, 6, so 8 to 3 really. But now at least I know that if you toss the coin 1,000 times, you should get, you wouldn't get in expectation 826. You'll get not more than 823. There is still an enormous gap with the lower bound, so it's interesting what else can be done here. And I hope there is no bug in my Mathematica program, but it passes various obvious checks that I tried, like, you know, like doing it separately for U and for V and comparing the answers. They give the same answer. But another interesting question here is how do you check this program that you know, that it's correct? But I think the method itself is quite new and quite interesting. So thank you very much. Well, like longest common subsequence, biologists call it alignment, and they attach weights to, well, for an alphabet of size 2, maybe not. For an alphabet of size 4, this is what every biologist does, well, what every computational molecular biologist does, they call it alignment, and they do it for genome assembly, they do it for lots of other problems. I still have a few papers with, even I don't know anything about biology, but I have a couple of papers with biologists who are using, you know, sort of related algorithms. Yeah. So yes, yeah. So I guess biologists would ignore all this, but they would ask, you know, what happened? What can we say about gamma 4? How much? Sorry?
How large?
How large? 8, up to 8. So, well, so this is 1, and this is 2, and this is 3, and 8 takes a few minutes in Mathematica. And I forgot to mention, I didn't have time to mention that there is another way of looking at this, which is, but the word diagram reminded me that this is a growth program, the growth process of a Young diagram as well. So it's extremely versatile problem that can be expressed in lots of different languages. Yeah.
Okay.